Connected to the server. Sweet. Hey, everybody. The toast joke. It was, so I often ask Siri or Alexa to tell me a joke. And today I said, hey, Siri, tell me a joke. And she says, I went to the zoo the other day and there was a piece of toast in a cage. A sign said it was bred in captivity. That's a great one. Boy, for those of you not here, there's dead silence in the room. Like just as if no one even heard that. Yeah, that's Maggie the dog. You guys asked for a picture of Maggie the other day, so that's Maggie. Maggie the dog. Must have been fall, we were hiking in the woods during hunting season, so she had her orange blaze on. So that didn't mistake her for a deer. She's a good girl. She's gonna be 13 in a few weeks. Yeah, that's the Maggie in all the lecture slides. I used to bring her in every semester to meet everybody at the end. So the last day, everybody come in, I'd bring Maggie in, just let her run around and say hi to everybody. But now she's really old and has arthritis and just has a really hard time getting around. But she still goes in the yard and we play and so on. But she's really, really old. So I can't bring her in anymore. Makes both of us sad. That's Maggie the dog. All righty. Oh, let me mention the midterm. So you guys did great on the midterm. Congratulations. The median and the mean were 90, 90, which I thought was just fine. Actually, great for that exam. I'll release the grades. I guess I'll go back to the office after this and do some work, and I'll release the grades then. So, like half an hour after this section is over, I'll release those to you guys so you can take a look at them. There was one question, I think it was question 22, that was a little ambiguous. That was the dereference pointer, and you're adding 5 to it and so on. And if you remember the question, actually prints 6, which wasn't on the list of your choices, and the other choice was unknown or something. And I can see how that might be a little confusing, except that everyone except I think one person got that one right. So I guess it wasn't an issue. I'll try to be a little clearer. I'll modify it for next semester for sure and be a little clearer in the future. What else is going on? Looks like the graders are still cranking through PS1. Be nice if that was done. So I'll have to crack a whip on them, I guess, to get those done and out for you, because PS2 is coming in too. And you're going to see PS3 assigned. I'll have to take a look at it and see if we've talked about enough stuff so that you can see PS3 yet. I think so. So you can look for that to drop tomorrow, and you'll have a week or so to do that one. Yeah, unknown was the answer. That was the one, Jonas. All right, cool. What else is going on? That was a typo. Now you're all trying to butter me up around my dog, huh? All right, here we go. We're still doing this stuff, right? All right, when last we met, just a really quick recap. So we talked about enums and unions in here. Actually, there was the one question on the exam that everyone did really poorly on, was the question about unions. So let me just really quickly remind you what a union is. Remember that a union it's a group of variables, but we can only store one of them at a time. So specifically, if we do this, so here's the union. The union it's a variable called info in this case. I've got 3 variables, int, a char, and a double. I can only store one of those things at a time. So for example, when I do this, I set info.age equal to 25. That's fine. When I do info.distance equal 123.456, that overwrites the memory that the 25 was in. And so where there was a 25, now I got 123.456, a representation of that float. The age is just completely gone. If I went back, if I did it again, if I set age here, the info.age on this line, that would overwrite distance. So you can only store one thing at a time out of the union. I can't really think of a good like real life analogy for that. There's got to be one. Got to be one. Maybe it's like, oh, here we go. No. So with A, always go with A, right? If you, let's say you have 3 eggs, and you've got an egg carton with 1 slot in it. It's an egg cup. I have an egg cup, and I've got 3 eggs. So the 3 eggs are the int, the char, and the double. I can take any of those eggs and put it in the egg cup. If I want something else in the egg cup, I got to remove the egg that I stuck in there and put the other one in. So if I put the int in the egg cup and I want to put the double in, I got to get rid of the int and put the double in. So the cup can only hold one thing at a time. The cup would be the union in this case. So they only hold one thing at a time. Jonas says, I thought everything would just be stored in every var. Not at all. So in this specific case, so this thing, remember union, the size of a union in memory is the size of the largest thing in the union. So age is going to be 4 bytes, char is 1 byte, that double is going to be 8 bytes. So the whole union is going to be 8 bytes wide. And within that 8 bytes, I'm going to write either age or a char at the front. The double distance will take up the whole 8 bytes and so on. So it just keeps overwriting, it's reusing the memory. It's like scratch memory almost. Janice. That derp moment, right? All right, so that's a union. We actually use unions quite a bit, and you'll see that I keep talking about the killer feature of unions. That's coming up on a couple of slides. Sam asks, would age be null or undefined? It wouldn't exist. It doesn't exist anymore because you overrode it with the distance. So it literally just writes the distance right on top of where age was.
Excuse me, Professor. Can you hear
All
me?
right, let's move on to structs. Structures.
What?
I just call them structures because it's easier to say than struct. We looked at a slide or so, or probably just the first few slides of this on Tuesday. So here's a structure. It looks just like a union, unfortunately, but they're really completely different. A structure really is a collection of variables. I can access any of them at any time, and the size of that structure in memory is going to be the size of the sum of all of the sizes. So here I've got, there's 10 chars, there's 30, that's 40 total, plus 30 is 70. There's an int for year, which is 4, so this looks like 74 bytes is the size of this structure. So when I create a new one of these, were you guys able to hear me? What? Actually, Jonas, I couldn't hear you. Did you just talk? I couldn't hear you. Oh, Jonas tried to ask. Yeah, we couldn't hear you in here for some reason. I don't know why. Just ask it on the chat. I didn't do anything to you. Yeah, so it's 70 bytes, the sum of all of those sizes. Now, in this particular struct, we're initializing it. So here's the name of the struct. Actually, this is an unnamed one. This is the type. So the type here is struct student. And we know it's a type because down here I use it like a type, right? It's just like an int. So here I might say int Maggie or float Maggie. This is a struct student Maggie. And in this spot, I am initializing some values, initializing all 4 of them actually, and they go in order. So BUID goes in the first one, Maggie's first name, Donham's last name, and 2 goes into the year. There's a bunch of ways to initialize these things and to access the values. You'll see a couple of them as we go through here. Yeah, well, so it printed out as 65, but that's like, who knows what that is, right? It's just some random bits happen to be a 65. Here is the struct in memory. Bip. And if we counted these, we should see 70. But you can see that, like that first thing, that's a U31, a 30 is a 0, so 31 is a 1, 32 is a 2, 33 is a 3, and so on. That was U1, 2, 3, etc. And then there's some space, actually no space, because that was pretty tightly defined. For the first and last name, there's 30 bytes allocated. That's what all the extra space is, 30 each for the first name and last name. And then somewhere in here, we're going to see a 2. Here's the 2 down here, right? Right there is the 2 for the year, 66 bytes away from the start. You guys are obsessed with that one, huh? Oops. All right, so that is the representation of this struct in memory. If I want to get to pieces inside the structure, I just use the dot notation, that access operator. So for example, if I want the first name, here is struct student. We're calling it Maggie. And Maggie dot first name gives me to the first name variable. Maggie dot year gets me to the year variable, and so on. So just use that dot access operator to get into the structure to visit any of the variables that are inside of it. If you initialize this way, by the way, that last bullet, you can't skip any. So I can't do, for example, this. That doesn't work. I can do the first one, the first and second one, the first, second, and third one, but I can't skip any in between. All right. If I want to set a single member, I can do it. Here, it's the same idea, right? So the type is struct student. Maggie's the variable. And I'm just going to initialize that first item, the user ID in this case, the BUID. And then later on, I want to set the year. So I just use Maggie.year. .year gets me to the year variable. Just set it to it too. And by the way, just for completeness, where we are, 15. I think I mentioned this on Tuesday. Structures are laid out in memory in the order that they appear in the declaration. So here I'm declaring this struct student. The layout in memory is going to look exactly like that. 10 bytes for the ID, 30, 30, and then 4 for the year. Most of the time, and I think, I'm going to guess, like for this class, we don't care too much. There can be situations where, depending on the size of the variables inside the structure, I might be concerned about a variable breaking across a word boundary maybe. Like if a word's 4 bytes, and I got something that's 5 bytes wide or 4 bytes plus a bit or something, I could waste space because I'd allocate a byte and only use 1 bit in it. Or if I'm working on word boundaries, I'd allocate 4 bytes and only use 1 bit inside of it. Whereas if I packed them a little more efficiently, I might use less actual memory. Again, I don't think it's something we have to worry about in the class, although we are going to do bitwise operations soon. We'll just have to see if it comes up, and if it does, we'll talk about it. But just keep it in the back of your head that there are situations where the order matters. Probably we're not going to run into them, but out in the real world, out at the work world, you might. Usually, if you're worrying about bits crossing word boundaries, you're doing some really, really low-level, serious programming. We don't do that sort of thing in here. It's just school. We just sort of wave our hands a little bit and hope you understand a little, and then we shove you out the door. All right. So we just did that. If I want several of these variables, like this guy, so this is the type is struct student. And now I'm going to create 3 variables here, Maggie, Fred, and Bob. Each of them is going to be a struct student. I could initialize any or all of those on this line if I wanted to. I might have an example of that on the next slide. Yeah, so here I'm initializing Bob, for example. So it's a struct student type. I've got 3 variables of that type, Maggie, Fred, Bob, and I'm initializing Bob's values, at least a couple of them. .buid is going to be that thing, .year is 3. Now this kind of, like building a struct this way, this is essentially an anonymous struct. It doesn't really have a name. It has a type, and I can use that type later on. I could name these also and then use the name instead of the type itself. So instead of struct student, I could just give it a name. We'll see how to do that in a sec. Question was, if you don't know how many struct values you want to create, how would you recommend going about doing it? Bernard, I would wait for about 30 minutes, and I'm going to tell you how to do it. That's what I would do. That's a great question. And that's actually more likely to happen, right? Because usually most of the programs we're going to write, like they're going to run and be interacted with, like we probably don't know how many structs we need. And so we're going to have to create them on the fly. And that's what we're going to talk about last in here. Actually, we're going to talk about that a little bit today, and then much more. That's a lot of what we're going to be doing in the next couple of weeks. I can nest structures if I want. In this guy, I've got a struct inside of a struct. The outer struct is called student. So that's holding everything. And then within student, I've got a name structure that has a first name and a last name variable inside. It's just organizational, really, right? So I'm just saying, you know what, I got this view ID up here, and I'm going to treat the name as a single unit. Maybe I've got some function that reads those two values and concatenates them for me. Who knows? To get to it, so that's a struct in a struct, right? So this is a student structure. I'm going to create a variable called Maggie of that type. It's a student type. And then if I want to get to that first name value, I first start at the outer level. So the outer level is this guy. So I've got this name variable here. So it's .name. And then within .name, I've got .firstname. So you just keep going down the dot list until you get to the thing you want. It's like an onion or a cake. What about this thing? Type def. This stuff makes sense, guys? I think it's, yeah, structs, it's funny, structs are pretty easy. Like once you've seen a union and you get your head around your union, the struct is like, oh yeah, it's easy. Yep, Nicholas has it. That's all we care about. All right, what about this? Type def struct. What is that? Type def. We're going to use type defs all over the place. And in real C code, like if you popped open the Linux source code in C, you would just see type def after type def after type def. We're typically type defing structures. Structures, again, if you open up the Linux source code, the C code, you're going to see structures everywhere. Like it's just, we should have called the language struct, because like that's what we write in. We just write a lot of structures in C. In the operating system code, most of those structures map onto physical things, like real things in the computer hardware. So I might have a structure that defines the registers on the CPU, and that structure is going to have a variable for every single register in the CPU, or some subset of them. We'll use structures for processes, like running programs. Don't know when we get to that in 2 or 3 weeks. But when we look at what does a program look like in memory as it's running, there's a structure called a process. There's a process header, which is another struct. There's a stack, which is another struct. All these structs come together in a big struct called a process, and that's how we represent like the running program. And we can get to any of those pieces through those structures. The question is, so if I want to define every field in a struct that contains another struct, do we still, oh, this is a two-part question. Do we still have to use the dot operator? Yes. Yes, you would use the dot operators to get to each piece, is how you would do it. Although, so pre-shadowing, since we're so close to COM, pre-shadowing, we're going to see that there's a slightly cleaner way to get to that stuff, at least the top level structure. You're still going to use dots at some point. So this type def idea is that we want to define a new type. Just like an int or a float is a type in C, we can define our own. And as I said, the most common thing to define is a structure. So what I'm doing here in this code, I'm saying, you know what, I'm going to define a new type for my code. That new type is going to be called student. I know this looks like, it looks exactly like the code on the slide before, where this was a variable name. Unfortunately, it's not. It's something completely different that looks exactly the same, which is like, welcome to C, right? So in this case, because I'm doing a type def, the definition is that. So I'm defining student as a struct, as this struct specifically. And then later on in my code, when I want to use that structure, I can just use student as a type, just like I would use it, use int or float. And I do it here. So here's the type def. I'm type defing a struct. This whole mess, I'm going to call that structure, that type definition, a student. And now I can say that, student Maggie. If I didn't have it, if I just had this, just struct blah student, I would have to say struct student, because the type here is, well, actually it'd be up here, right? So the type in that case would be struct student. If I use a type def, I can avoid that and just say type def struct, and then that's my type, and I just use it here. Let's use it here. So type defs like this, again, you're going to see them over and over and over. So like, if it doesn't quite make sense now, it's like, it will. You just see it so often that you'll get used to it. All right, so we use, as I said, we use just everywhere. We use them everywhere. The disadvantage to type defing is that if I'm reading code, if I'm 5,000 lines deep in a driver somewhere, and I see student Maggie, like the name of the type gives me a little bit of information, but it really doesn't tell me what's in there or anything. Like an int or a float, I know what those values look like. If it just says student Maggie, I'm gonna have to go look up the definition to see what actually the variables are. There's just no way around that, really. I guess it's the same with objects, right? If I'm using an object-oriented programming language like C++, those objects just have names. I still have to go look to see what's inside them. So I guess it's no different than that. It can lead to, especially if you call your types, A, B, C, and so on, like I would just fire you on the spot if I saw that. Like nobody has time for that. At least name them something that makes sense. Yeah, so actually that's why we use so many of them. There are no objects, and so we use structs instead. With a lot of limitations. Like there's tons of limitations on structs. We'll come up, we'll see those in a sec. So that killer feature. Everyone cool with the structure idea? Sounds like yeah. So the killer feature, let's say I've got a structure, and the example here, actually, it's similar to the example in your book. I want to have a structure that I use to track items that I sell. I've got a little store. It's just a small shop, not anything big, but it's it's mine. So I've got all the stuff I sell, and those things are different. Like I might sell books or coffee mugs or t-shirts or whatever I'm selling. They have similarities, they have commonalities, right? So they all have a price. They probably all have a part number in my system. Maybe they have a weight or something, who knows? Like they have common items, but some of them are really different. Like a book is different from a coffee mug. A book has an ISBN number, has a number of pages, an edition, et cetera, all the book stuff you might think of. That's really different from a coffee mug. Coffee mug has a volume and a color and maybe a logo on it, who knows what it is. If I built my inventory system to keep track of all of the things that I sell, and I kept track of each item in a structure, I'd have to have variables for everything. I'd have to have a variable for color, even if it was a book, and that kind of didn't apply. I just have all these variables in the struct and just fill in the ones that I was using for that particular item. I mean, there's nothing wrong with that, right? They run perfectly fine. The disadvantage is that when I built one of those structs, the size of it would be the size of all of those variables at once, summed together. That'd be that struct sitting in memory, it'd be this big honking struct. And maybe if like I had, I don't know, a puzzle or something that had 92 different variables associated with it, and I sold one of them a year, I'd still have to have all those variables in memory, even though I only used it once a year. Like, this is really wasteful. So I can do this. So I'm type defing it. I gotta remember to change the words I use here. I use item all over the place. I don't know why. I guess I was just running out of words that night. All right, here's the type def. The type def itself is called underscore items. So that's going to be the new type. It's a structure. Here's the common stuff. So everything's got a part number and a price. But now I take advantage of the union. Remember how unions work? I can only store one of the things in the union at a time. I can only store one at a time. The storage for that union is going to be whatever the largest thing is in the union. But, I mean, this is a small example. Think of a larger example where one of these things, had several items in it. You're going to save space, essentially. So what's in the union? Structures. I got two structures sitting inside the union. I can only store one of these structures at a time. And which is the big one? So that's 4 bytes plus 4 bytes is 8. That's 8 right there, plus 1 for the enum, so that's 9. So the storage for that union is going to be 9 bytes. It's not going to be 4 plus 4 plus 8 is 16, and 1 for that is 17. It's not going to be 17 bytes. It's only going to be, whatever I said that was, 9 bytes. So I'm saving a significant amount of space. When I use it, I just have to keep track of which of those two things I'm using. Is it the book or is it the mug? And because I've given them names like this, I wear glasses in here, do I? I've given them variable names, book and mug, and I can refer to them as book and mug inside the structure, the outlying structure, this one. So I'm going to have underscore items dot book, underscore items dot mug is how I'm going to get to those things. And of course, I'll also have underscore items dot price and dot part number. All right, I actually called, I called it something else, didn't I? This whole thing is called item. So it would be underscore items dot item, because this whole union is called dot item. And within dot item, I would have dot pages, dot addition, dot capacity, and this enum, which I didn't even give it a name. Probably should have. Let's see how it looks in code. Gosh, I don't think I wrote any code. Here's how you get to it. So underscore items is this. It's a type def, right? So I have a new type in the system called underscore items that is this whole structure. So underscore items, underscore items item. That gives me a variable called item that is this type. So it's the whole structure. And then from item, now I can go in and just traverse down that structure to get to the stuff I need. So item is the variable. That's the variable. Underlying that is, where's our struct? I've got this thing called item. That's this whole thing, that union. So item dot item gets me to the union, dot book gets me to the structure inside the union called book, and book has a dot pages, so now I can set dot pages in the book. If the very next line of code did this, item dot book, dot mug, dot, was it volume or something? What did we say it was? Books or mugs have capacity. Capacity. 1, 2, 3, like that. Poor choice of numbers, right? If I did that, what happens to book.pages? It's gone. It's gone. It's overwritten. How to get 9 bytes in memory, asks Sajna. The 9 bytes came from, so remember union, the size of a union is the size of the largest thing in the union. I've got 2 things in the union, this struct and that struct. This one is 8 bytes, because each of these is 4 bytes. 4 plus 4 is 8. This one has 8 for the capacity, and then there's going to be 1 for the enumeration. Since it's really, I'm sorry, I take that back. The enum is an int, right? So that's going to be a 4 bytes there. So it's going to be 12 bytes for that guy. Yeah, Bradley's got it right. What happens when I do this? Book.pages is overwritten. Just writes right over it, because I can only have one of those things at a time. I thought enums don't take space and memory. Well, I'm eventually going to use that somewhere, because it ends up being an int. At some point, I'll have to have an int. I'm not even certain, to be honest with you, that I can do that legally. That enum, where'd it go? This one. I'll have to try that in the compiler and see if it complains about that. Because normally that's just a label, right? So I'd use that label somewhere else. Maybe I'd do it this way. Yeah, I don't know. I'm not going to mess with it. I'll try that in the compiler and let you guys know what it looks like. All right, so that's how we get to them. And as I say, it gets deep pretty quick. Like all these dots, I've got a struct inside a struct inside a struct inside a struct inside a union and so on. Like there's a lot of dots going on. There's just no other way to get to them. And this is the big win. If I didn't have that union, as I said when we started talking about this, I would have to have a variable for every single one of those: color, weight, volume, pages, ISBN number, etc. I'd have to have all of those in the struct. They'd all have storage and memory allocated. I'm just wasting space in that case. So that's kind of the killer feature of unions. When I build them inside a struct like this, now I can have sort of the common items in the struct and then individual items that are specialized, but I can use the whole struct to store anything that's one of those union members, because each time I store one of them, it's only going to store the pertinent information for that thing, for the book, for the mug, whatever it happens to be, along with the common stuff that we defined. Got it, sweet. Arrays, how about an array of structures? I mean, a struct is just, especially if it's type def, like it's like any other type, right? I can have an array of integers, an array of floats, an array of strings. Here I'm doing an array of structures. Let's take a look at this. And this should make sense now. Here's my struct. I'm type defing it, so I'm gonna have a type. The type is student. So now I've got a new type in the system called student. I can use student anywhere in my code. In fact, I do right here. And this sets up what? An array of student type that's 5 wide, and it's called students. So I got a students array, it's got 5 student structs inside of it. And then here I can just set the name. Student0.name.firstname is Fred. Or at least I can try to do that. The compiler would shout at you. It will not let you do this, unfortunately. And here's why. Is this even on? That's pretty useless, huh? Let me turn it up. So here's the problem. Oh, sweet. Nice. A little better. Not much better. Here's the problem. Student 0. So Fred is a character pointer, right? When we define a string, it's really a pointer to a bunch of characters in memory terminated by a null. But what's student 0 really? It's really, here's my student struct. It's kind of it's not really a string sort of, there's no pointer here. I mean, first name kind of has a pointer to the first item, but it's a char, it's not really a string. I can't assign a string to a char pointer. It just doesn't work, because what's inside of a char pointer? Char pointer has the address of something, right? Because it's a pointer. Assigning a string to that, it's like, that looks really, really ugly. The compiler won't even let you get past that line. So instead, if we want to set a value inside that array, we got to use different syntax. We've got to do it not this way. We have to do it this way. Oops, we have to do it. Oh, there it is, derp, stir copy. Stir copy is in the string library, string.h. You're going to use string.h quite a bit as we work with strings because, as we saw it actually on Tuesday, you can't, and here it is again, I can't just assign a string to something that's a char array, like it just doesn't work. And so I've got to really just take that string and move it into the correct memory location that's pointed to by first name in this case. So first name is just the address of some location in memory. Stir copy copies the string into that location. And that's what's happening here. I'm saying, here's the target into student 0 name.firstname. First name is just a pointer to some byte in memory. At that location, copy the string Fred. And stir copy does the right thing for you. It'll put the \0 at the end. It'll actually return information to you. And by the way, just a quick caveat, the code we're looking at today, there's no error checking at all. Most of this, if I tried to put this code in production, I would be fired. Most of C is writing all the checking around all this stuff. Because remember, it's all done manually, right? So if I try to do a stir copy into this location, that location, and it fails for some reason, and there's a number of reasons why it might fail, stir copy is going to return a value to me telling me whether that succeeded or not. And I would need to do this and then immediately test that return value to make sure that the copy was successful. And if not, do something about that. So we'll run into stir copy quite a bit. I'm not going to spend a huge amount of time on it because we'll see it again. How about pointers? Because you know we're in C, right? We just want to play with pointers all day. That's kind of what C is. How about pointers? So here I was using the dot operator in this stir copy command. Student 0, which is the first item in the array, dot name, dot first name, and then setting it to Fred. If I want to use a pointer for this, I mean, we can for sure. I've got a pointer, right? It's easy to get a pointer to it. So let's look at this. Here's my struct. In this case, I'm not type defing it. So I've got a struct person as the type. I've got a variable called foo of that type. And now I'm going to create a struct person pointer. So struct person pointer foo p. I'm going to give it the address of foo. So foo p at that point is a pointer to the structure, to the first byte of the structure. And now I want to set the age. It looks like that. It's not horrible. The problem here is that the dot operator has precedence over the dereference operator, which I've been writing C for 30 or 40 years at this point. I have never understood why. No one's ever been able to tell me why. I would think dereferencing would be right at the top of the list of operations. You do always that one first, but no, dot has precedence over star in this case. No clue why. Anyway, so if we did it this way, if we did it that way, dot age would fire off first, and then we're trying to dereference something that's that thing. It's like, oh, it'd just be awful, wouldn't it? And so we have to tell C, hey, do this first. That's what the parents do. So this bit dereferences the pointer. Remember that pointer's pointing at this person thing that is in foo. And then once I've got the dereference, that gives me access to the structure. Now I can do dot age and just set it. And the same thing here, I'm going to print it out. So because dot has precedence over star, somebody in A1 had some really clever PEMCAC or something that they used to remember the order of precedence. I can't remember what it was. But same thing here. I got to dereference first, and then I can get to dot age. Yeah, the good news is that you probably won't use that structure, that way of writing it very often. This just tells you why. There's a much more intuitive syntax. You're still going to have to use dots, unfortunately. Um, but you can avoid this whole star foo p thing, inside the parents by using an arrow instead. This guy. So the arrow operator dereferences a pointer for us, and it does the right thing. So we don't have to put it in parents or anything. It knows, oh, I'm using an arrow. I'm dereferencing a pointer. Oh, look at this. Maybe I'll dereference the pointer and then do whatever came after that. So essentially, I guess the arrow operator has precedence over the star operator for dereferencing. This does the same thing as we saw earlier. So I still have a person, struct person pointer that's going to be pointing at foo, that structure in memory, but then I can just do that. So it's a foo pointer, it's a struct person pointer, point it to the age variable and just set it. And the same thing printing it out, that works too. That's the notation I'm going to use going forward. Yeah, question.
What happens if the dot operator is at like more
I didn't need the dot operator in this case because age was at the top level of that struct. And so when I dereference the pointer, I'm looking at the top level, and then the arrow points me to the age guy inside that struct. So it's basically starting from the dereference and saying that arrow kind of points to the thing you're interested in. Yeah. Now, if I had a struct inside of age, maybe like, century or something, then it would be the foo-p arrow age dot century. Because it would just be a struct, it wouldn't be a pointer inside. Why do you, oh, Sergey, why would you use a pointer with structs? It's like the only way we work with structs in C. And so C is pointers. If you don't like pointers, you shouldn't be writing in C because that's all we write in C is pointers. And those pointers are almost always pointing to a structure in memory. So we use structs and pointers constantly. Think about C++, right? So C++ is object-oriented. What am I using arrows for in there? Pointing to objects, right? So I create an object, it gets stored in memory, I use a pointer to get to it, use the arrow notation. It's exactly the same thing. It's just that we don't have objects in C, we only have structs. So the struct becomes kind of our pseudo object in that case. But yeah, Sergey, we just use them all over the place. And I think because most of the time we're creating new structures as we need them. And when I create a new structure, you'll see this in a few slides, and somebody else asked about it earlier. When you create a new structure, we need to allocate memory for it. We're going to use the malloc command to do it, or a realloc or one of those, calloc. So I get a chunk of memory, and to get to that stuff in memory, I need a pointer to it. So if it's a new struct I just created, I need a pointer to the struct. You're welcome. Sergey's like, okay, please stop talking. All right, so we're going to use the arrow pointer the arrow notation going forward. It's just a cleaner way to write it, I think. I mentioned the other one, but we talked about the earlier one, this thing. There's tons of that in code. Like you walk down the street and walk in any office where they're writing C, you're going to see that notation. There's nothing wrong with it. It does exactly the same thing, but we're replacing several characters with the arrow. And honestly, for me, I wrote C a long, long time ago. And then most of my work in this sort of zone was in C++. So I got really used to using arrow notation in C++. When I came back to C, it's like, yeah, of course I'm going to use that. Why remember two things? I just have to remember one. Here's the same thing with type def. So as this bullet says, if I'm going to use a structure more than once, and that's usually the case, I'm going to type def it because now I can just use that as a type. So here's the type def. The name of the type is person, and it's a struct. It's this struct. So later on when I need it, I just say person foo. And because I've defined person as a type using type def, now foo is of type structure with those two variables inside. it looks exactly the same once I get past that. Really, the only change is here. Actually, here too, because I can use person pointer instead of struct person pointer. But then it's the same, right? So I get a person pointer, call it foo_p. It's got the address of foo in it, and then I use that pointer to get to the age variable and set it. And here I'm using the pointer to get to the age variable and print it out. So some limitations, as I mentioned, we don't have objects. There's no access modifiers. There's no public, private, protected, any of that stuff that you're used to in Java or C++, or I don't know if Python has that. I assume they do. There's no hierarchy. So no inheritance whatsoever. None of that. It's really just variables inside a container. No functions. No functions inside a struct. Although you could probably get around that because a function is just some code in memory, right? I can take a pointer to a function. That's actually, we do that quite a bit. Take a pointer to the function. So I could have a function pointer sitting inside the struct. The struct wouldn't have a function itself, but I could fill in that function pointer later on when I initialize the struct, say, hey, that function pointer, what I mean by that is go and hit this function that I'm pointing to. That's a really common thing to do. Like you'll see situations where actually like a case, you could, oh, wow, what a great homework assignment. So remember that old calculator you wrote, PS1? Use that case, that switch statement, right? All those cases. You could do exactly the same thing. Instead of calling the functions, you had a function called added, one called subtract, and so on. You could instead of naming those functions, write all those functions, add, subtract, multiply, but then have an array of pointers back to those functions, and then your case statement, your switch statement, would just examine the, how would I do it? I would examine the operator. I would use the operator as an index into that array. The array has a bunch of function pointers in it. What comes out of the array is a pointer to the function that I want to run based on the character. So if it was a plus, what's a plus in ASCII? Let's make something up. It's like 65 or something. So I would just I would normalize it. I would subtract 60 from it and get a 5. And that would be the fifth thing in the array. The fifth item in the array would be a pointer. The pointer would point to the function to do the addition. That's what's returning out of that array. And then I would just execute that function with its parameters. I think I just invented PS4 or maybe even PS3. That'd be, no, we haven't talked about function pointers. Ian says, Ian, I love your name, man. It's a great handle. Is it better to use typedef all the time? Thinking. I tend to use typedef all the time. Yeah, and the only reason I don't is if I know that I'm just doing like a one-off, like I need some scratch memory somewhere, and I'm gonna, spin up a real quick struct to hold something, but I'm only gonna use it once. So if it's a throwaway struct or some other type, yeah, I won't typedef it. But if I even think that I'm going to use it more than once, I'll just typedef it. And to the point where I probably just typedef everything. And then the exception would be, oh yeah, I'm only going to use this once. I won't typedef that one. Yeah, so there's a lot of limitations on structures. But like I said, like the function thing we can work around, right? Access modifiers, that's a trickier one. We just don't write object-oriented code in C. End of story. If you want object-oriented code, you write it in C++. Or Perl or Python or Java. Not Java. Now let's talk about the fun stuff. I can't recall who asked this. Probably Jonas. What about, or Sergey, what about the situation where I don't know how many of them I need, which is most of the time? If it's an interactive program, let's say it's like a contact card list, and I want to add a new card to the contacts, say give me a new one and type in the name, address, and so on, and store it. Like I can't predict really ahead of time how many I need. I could try, but it might be wasteful. let's say I said, oh man, this is going to be so popular. I'm going to have 10,000. So I just set up an array of 10,000 of these structures ahead of time. And then like, it's not very popular and people only use 5. Well, I've just wasted, 9,995 locations in memory because they're just sitting there with nothing in them. It'd be much more efficient if I could just build that array out on the fly. Every time I need to add a new one, just add one. And then it's exactly the right size all the time. So that's what we're going to do. And this is just a taste, by the way, just a little tapas of dynamic memory allocation. We're going to look at it a little more closely next week. And like the course essentially is this. Like we're just constantly going to be pulling stuff out of the heap, managing it, returning it to the heap. It's just C. We work really tightly with memory in C. And this is one of the ways that we do it. So we're going to build something new and stick it into memory as we need it. Let's do an array of structures. And so the caveat on this code that you're about to see, do not ever attempt to do something like this in production code. I would be fired on the spot if I handed this in, to my managers like, oh, let's push this to prod. You're fired. And why would you fire me? And he'd show me the next slide. So there's no error checking. Error checking is tough. I don't like talking about error checking all that much in class because you essentially have to do it on every single line of code. Anytime you're using memory, you're allocating, deallocating, writing into memory, reading from, well, not reading usually, but anytime you're manipulating memory, you absolutely have to check to make sure that it was a successful operation. It's usually a couple, 3 lines of code to do it. It just takes a lot of time to talk about it. I mean, we'll get to that, of course, because we have to. I just avoid it a lot because it's just extra code. Like this code was going to take 2 pages if I did all the error checking on it, and I wanted it on 1 page. So it was style over function in that case. All right, so here's what we're going to do. We're going to pre-allocate the array in this case, which is kind of cheesy, but it works. So we'll pre-allocate the array, and then we're going to fill in structs on the fly as we go. Here it is. Blah, blah, blah. Here's a struct. So I've got this struct up here called person. Why did I do that? Oh, I was going to call that from somewhere. That's why I did it that way. It looks slightly different in the code in C line. So here's a struct, right? I'm type defing it, so I've got a new type called person. Here's where I'm going to allocate the array. I'm going to take a person pointer. That person pointer is going to be called people. And I'm going to use malloc here. Malloc is memory allocate. I'm going to pull memory from the heap and allocate it to my program. I'm going to store the first byte of that, the address of the first byte of that allocation is going to be stored in the pointer. We haven't talked about it. We will, of course, in the next week or two, how programs are laid out in memory. Programs, generally speaking, there are 2 areas where you can grab memory from. So when I do something like, of course, I didn't do any of them in here. I do this, like int foo equal 5, that. The storage for foo is, and you'll hear all this again later, so don't feel like you gotta write all this stuff down. The storage for foo in this case is built into the program essentially. There's an area in your program in memory where these kind of pre-allocated variables go. It's the data portion of your program. So they're like pre-assigned. If you look in memory, you'll see, oh, there's a big chunk for all the variables. There's all their names and or all their symbols and their values and so on. That's if I do it this way. If I'm doing them on the fly, that comes from a different location in memory called the heap. The heap is just a bunch of unused memory that's been allocated to our process, and we're going to draw from that as we need it. So we're going to take memory off the heap, use it in some way, and then when we're done with it, we'll return it to the heap so that I can use it somewhere else in the program. So the heap is the dynamic stuff. That other portion, which is sort of pre-assigned for things like int foo equal 5. We have to manage the heap. So there's nothing done for us. Like anytime we're using the heap, you're in charge and good luck, is what C says. All right. Where were we? We're here. We're here. So I've got this person type. I've got a pointer, a person pointer called people, and I'm going to allocate memory for the entire array. In this case, the size of the array in memory is going to be 5, because I said my number entered is 5. So I'm going to have 5 elements in the array. The size of each of the items in the array is going to be the size of a person. So I've got 5 persons in the array. Person is, what, 4 here, 4 there. So it's 8 bytes. So it's going to be 8 times 5. I'm going to have 40 bytes of memory allocated. malloc returns a pointer to the first byte of that. So this pointer, people pointer, this person pointer people, is going to have the first byte of that chunk of memory that we just allocated. And I got space for all this stuff. Then I'm going to hold a temporary pointer, like just this is going to keep track of where I am in that memory. I'm going to set it to people because I want to maintain people. Later on, I'm going to go back and use people, but I need to muck around, like move around in this memory, use this temporary pointer to do it. And then finally, I've got this person pointer called person P. That's going to be an individual person inside the array. Count its number entered, so that's 5. Now inside this loop, I'm doing a couple of things. Inside the loop, I'm going to allocate memory for one person. So the size of person is going to be one of these guys, 8 bytes. So I get 8 bytes coming out of malloc, and a pointer is stored here in person P. That's a pointer to that 8 bytes. It's a pointer, so I can set age. In this case, I'm using count as my age, just so we can keep track of them in memory. Why can I set age? How does that person underscore P doesn't know there's even an age thing in there? Zoom set. Susrita says, would that char be 5 instead of, because no, it's just a char. There's nothing stored, there's no string, so it's just 4 characters. So if you wanted to store a string in there, it'd be 3 characters and a \0. It knows about age because what's the type of person P? Person P is a person pointer. Person is this type, and so it knows there's an age value in there. So I can use that arrow notation here. I just allocated memory for it here. I've got a pointer to that 8 bytes. Go and set age to count +1. And then that people temp pointer, this guy, I'm going to bump up a little bit. And then I'm going to set that equal to the value at person P. So that's going to be an address, right? So this guy is going to end up with basically the next address. And then when I'm done, I'm just going to access it like this. So I'm going to basically dereference that thing. People's going to have an address in it, or people's going to have a struct in it. I want to go, sorry, people is the array. So I'm going to go from that spot up to, it's going to go up to people from that spot, and then print the age out there. Let's go look at it in C-line. Sergey, malloc is memory allocate. So malloc will give me a chunk of memory of a certain size. In this case, the size is 1 person times however many people I want. So if a person's 8 bytes, I got 5 of them. That's 5 times 8 is 40. You know, I think I was using that just to keep track of stuff so I could like show stuff in C-Lion. Can't remember if I actually use it or not. Am I manipulating people down here? Person P, says a person. Oh, no. This is actually, sorry. Yeah, I got lost too, Ian. This line actually puts it in the array. So look at what people temp is to begin with. People temp points to the first item in the array. And then here I'm saying, you know what, the value there is the person P thing. Person P is the new person that we just created. So this person P, this puts it in the array position. It's not, I'm not dereferencing really, it's the value of that thing is one of these people. It's the address of that person. Yeah, exactly. And then Jonas, and it increments afterwards. Here's some memory. Or running. Stop. It's the same idea. And actually, Jonas, since you mentioned that, let me just point that out. So this construct that I used, I go back and forth. It's like, should I use shortcuts like this in class? And then I think, yeah, because when you're writing code for real, you're going to use as many shortcuts as you can. And if you see them now, like you'll remember, and maybe even start using those shortcuts. I'll become part of your toolbox. So look at what happens here. So this is a while loop, right? Here's the bottom of the while. There's the while loop from there to there. Well, count. Well, count, it starts out as a 5. The way this works with the minus minus after the while, this is saying while count, it's going to look at the value of count, and then it's going to minus minus it. If I'd done it this way, it would subtract 1 from count and then look at it. So I'm just using that as a cheesy way to do count equals count minus 1. So I don't have to do it down here. So that'll take care of decrementing count from 5 down to 0. Actually, from 4 down to 0. And then these guys, like this one. So the value of people temp plus plus, that happens, and then that happens. So I'm going to place something in the right spot and then bump the spot up 1. So the next time I go through the loop, I'm pointing at the next thing. I do that quite a bit, actually, especially around decrementing and incrementing. I'll think about, especially loops, like what am I keeping track of? What do I need to increment or decrement? What does it need to look like on the next pass of the loop? And try to write code that looks like this so that that saves me 2 lines of code because I don't have to manage decrementing or incrementing stuff. I just do it right there on that line. And because of the way plus plus and minus work, they're unary operators. Depending on which side of the variable they're on, you have really fine control, I think, over what happens when. I would actually encourage you to start thinking that way and start writing code that looks like that. I'll post my solutions to PS1 for you once they're all graded, or PS2 rather. It looks the same. So some of those loops in PS2, I do them like this. You end up with just like 1 or 2 lines of code. All right, so let's take a look. Let's stop it here. It's gonna rebuild this. Build, very nice. Go debug it. Now let's take a look at, we've already been through the loop 5 times. So let's take a look at that people array. Here's people in memory. And you can see where they fall. So we said they're 8 bytes, right? So there's 8 bytes. And you can see that one's been set to 5. So age was the first thing in the struct. There's the 5 that we set here. The next one's here. So that guy is the 4. Here's the 3. 2's to the right of that one. 1's right below it, and so on. So those are all my guys. If we look inside, here's the people array. Well, people just points to the first one. So that's the name of the very first one, I guess. And what was people temp doing? Yeah, it's really the same. You don't have any names, you just have ages. At that point, people temp is not really used. And here's where the error checking comes in. Like I've done some really bad things in this code. Like I would flunk this class if I did this for real. Anytime I use malloc. So here I malloced out, actually here. So I malloc out the size of a person, right? So I get a pointer to that. Really what I need to do is when I'm done with these pointers, I guess I'm not really done, but when you're done with them, you need to release that memory back to the operating system, back to your program, and you would use, there's a couple of ways to release it back. You're essentially just putting it back on the heap. If you don't, you run the risk of, actually this is one of the biggest risks of C, you run the risk of grabbing a pointer to a chunk of memory and then losing track of the pointer. Use the pointer for something else, but that chunk of memory that you allocated, you didn't deallocate it. It's still sitting out there in memory, but it's like, I use the example of George Clooney in A1, like it's George Clooney in Gravity, right? So, you know, George is out in space in his spacesuit. He's floating around out there. He's there. He's taking up space, but you can't get to him. That's the same thing as a memory leak. Here, if I'm not managing these pointers very well, it sort of works out because it's a short program. I don't reuse those pointers. But you know, it's like you got to take care of the pointers when you're working with memory like this. What was the question? It says, in this case, is person underscore P really necessary? How would you get rid of it? I think it is, because really what person under P is, it's pointing to each individual person as I create them. So that malloc is going to return the address, the address of the first byte of an 8-byte piece of memory that's been typed to person. I don't think there's any way around that one. People temp, maybe I could, actually no, I can't really, because I'm using people down here, right? Yeah, I can't even get rid of this people temp one either, because people is pointing to the first byte of the original array that I allocated. But here I'm manipulating a pointer. I'm moving up and down that array. At some point, I'm going to lose. In fact, after the first iteration of that loop, I'm going to lose track of where the first one was. I guess I could minus my way back, but that's pretty risky. So I need a pointer that always points to the start of the array. I would call that one people. And then I can use that temporary like scratch pointer to move around. I still have a reference to the first byte of the array, so I can always get back to my array, which is what I did here. Let's just run this and make sure it actually prints out what, +2. It's going to be like I don't know, how old is that one? Come up. Person at 2 has age of 3. Let's go find out if that's true. I'll debug it. And let's go look at people. I'll look at location 3. So that's 0, 1, 2, 3. There he is, right there. He's got a 2 in him. This would be the 0 one, because it's an array. It starts at 0. Next one would be 1. There's 2. There's 3. We're starting to get closer to like the code you're going to end up writing in the class. Like to this point, it's been kind of basic stuff. And now we're getting to the meat of C. And it's the interesting part of C, I think, like really twiddling bits down to really low levels. So it's going to start looking like more and more like this as we go through the course. All right, sweet. Is our bottom line over here somewhere? Yeah, zero help. You get 0 help in C. Oh, and I'll just mention this. I forgot to mention this in A1. Anytime I'm working with pointers, I've got either a whiteboard or a piece of paper in front of me, and I just draw boxes and arrows. So I'll write down the variable name and then draw an arrow to some box and say, oh, that's a person. And then I'll draw another arrow, you know, the temp pointer pointing to that person, and then another arrow pointing to the array. I use a whiteboard, excuse me, to keep track of where the pointers are pointing to. And I'll just walk through you did this in CS111, right? You hand walked through code and saw what each variable was at every line. I do exactly that. And I've been coding a long time. I still do it. I usually use a whiteboard because I've got a bunch of whiteboards around me. But that way I know exactly, I can just go through every single line of code and draw it. And then I know where the pointers are pointing. And it's obvious when you do that, oh, where's this pointer pointing? Oh, it's pointing to nowhere. Oh, I need to get back to that spot. Where's the pointer pointing to it? I don't have one. Like it's really easy to see visually that, oh, that's a memory leak. That's what a memory leak looks like. All right, so bottom line. Really string primitive types? How do we get there? That's the bottom line from the last lecture. I didn't write the bottom line slide. Well, the bottom line in this one is that in C, structs are king. You're going to be writing structs out to the wazoo. We've seen that the union can be used as a way to save memory. And in fact, we use unions like that all over the place for that very purpose. I mean, think about the code you're writing. You're writing operating system level code. You're writing drivers. You're writing embedded code. In almost every case, every byte matters. Like the operating system is not real work, right? That's just bookkeeping, essentially. You want that thing to be as small as possible so your applications have more room. So we use these features that we talked about this week over and over and over again. And I guess the second thing in the bottom line is we just have to be really careful when we do it because we're doing everything by hand. It's really easy to skip a step and your program is going to crash, or even worse, it's going to do something unexpected. It's not going to crash, but it's going to screw something up pretty badly. Those are the worst errors. Those are hard to find. All right, I will go write another bottom line before I post this for you guys or repost it. All right, that is all I've got. Look for your midterm. It's being posted. Scores will get posted in about half an hour. And PS3 is coming up soon, probably next week. Yeah. Yeah, and I'll prod them again today. They're a little slow. So PS0, here's the dirty secret of PS0. If you did PS0, you got 100 on it. The way we wrote it in Gradescope and the way it was parsed out in Gradescope, it's a nightmare to grade. Like every single line is a separate thing to grade, and there's 250 of them, and there were like 12 questions. So there are thousands of these stupid things to grade. So really, I mean, that assignment, PS0 was about you guys getting your environment up and running. And so if you manage to do something like that and manage to get something into PS0, we're giving you credit for that one. And PS1, I'll crack the whip, and because you guys deserve some grades. All right, that is all for today, 3:15. That's it. Have a great weekend. Go in peace. Enjoy. I'll see you on Tuesday. Tuesday. Oops, not that one. This one, right?